All right, this is video number 3 in equilibrium. We're looking at question L. They give us a couple of reactions and a couple of equilibrium constants, and we need to determine the Kp for the following reaction at 700 degrees Kelvin. And you can look and see that this is kind of a takeoff on a Hess's law problem. Our reaction is 2 ammonias plus 3 iodines is in an equilibrium reaction with 1 nitrogen plus 6 HIs. So we can see that in order to get this last reaction, I've got to multiply the first reaction by 3 in order to get the 3 iodines. So therefore Kp for the first reaction would be 54, our Ka raised to the third power. And I need to reverse the second reaction to get the 2NH3 on the correct side of the reaction. So that makes my Kp equal to the inverse of 1.04 times 10 to the minus fourth. And so when we add these reactions together, we multiply their Kp values. So when I multiply 54.0 cubed times the inverse of 1.04 times 10 to the minus fourth, I get 1.5 times 10 to the ninth. Well, this is a very large K value, so our reaction is heavily favored to products. All right, section 15.4, heterogeneous equilibria. Question A. What happens when we have a chemical reaction that involves a pure solid or a pure liquid in a heterogeneous equilibrium? Do we include the concentration of that substance in the equilibrium constant expression? So here's our first example. We have calcium carbonate solid reacting to form calcium oxide plus carbon dioxide gas. All right, so the equilibrium constant expression for the reaction shown above is written as Kp is equal to the pressure of carbon dioxide. And that's it. If I was doing this from a concentration perspective, I would just write the concentration of CO2. But since it's a gas, we prefer to use the pressure. So the answer to the original question is no. We do not include the concentrations of solids or pure liquids, such as water, in these equilibrium expressions. We leave them out. All right, so now we're looking at question C. As you can see in figure 15.7 on page 623, which I put on the right-hand side, the pressure of carbon dioxide in the equilibrium system at a certain temperature is the same, no matter how much of each solid is present. So now we go to question D. It asks us to write the equilibrium constant expressions for each of the following heterogeneous reactions. You should at this point have a pencil or pen, and you should be writing these. Probably the first one would be relatively easy, and then you should go and do these before you see my answers. So when we look at the first one, we're going to take just the gases or the ions and leave out liquids and leave out solids. So that gives us carbon dioxide divided by the concentration, carbon monoxide divided by the concentration of carbon dioxide and hydrogen. When we look at the second one, this is only going to be the concentration of carbon dioxide squared divided by the concentration of carbon monoxide squared, leaving out the solids. For reaction number 3, now when we look at this, we take chromium ion raised to the first power, leaving out the silver in the numerator. In the denominator, we have silver ion raised to the third power because the stoichiometric coefficient is 3, leaving out the chromium. In the fourth example, our equilibrium constant is going to be the concentration of ammonia times the concentration of hydroxide divided by the concentration of ammonia. We leave out the liquid water. We do include the liquid ammonia that is dissolved in the water. So that part is included in this equilibrium expression. All right, section 15.5, calculating equilibrium constants. We want to explain how to calculate the value of Kc if the equilibrium concentration of all the reactants in the products are known for some particular reaction. We're going to plug in the concentration, or if they're gases, we'll plug in the pressure values at equilibrium into your equation and solve for the equilibrium constant. So we need a balanced reaction, we need an equilibrium expression, and we need some way to calculate what those numbers are. So in some situations, you don't know what these are, but you might know the initial concentrations of all the species, and you know the concentration of at least one substance at equilibrium, and you can use the stoichiometric relationships to figure them all out. We're going to use a very powerful tool called a Rice chart to help keep track of all of the quantities in these relationships. And of course, we have to ask ourselves, what does RICE stand for? R is reaction, I is initial quantity, C is the change in quantity, and E is the ending quantity, or the equilibrium quantity. Now, when I make these tables, I normally put the reaction at the top of the chart with a box around it. So you'll hear me use the expression rice box. So we're going to take a look at an example here. Sulfur trioxide gas decomposes at high temperature in a sealed container to produce sulfur dioxide gas and oxygen gas. And the reaction is at equilibrium, or it's an equilibrium system. So first part, right, we need to write a balanced chemical equation for this equilibrium system. So I've got sulfur trioxide, which decomposes to sulfur dioxide plus oxygen. And when I balance it, I get this. So this is my reaction. Initially, the vessel is charged at 1,000 kelvins with sulfur trioxide gas at 0.500 atmospheres. And at equilibrium, the total pressure in the reaction vessel is 0.650 atmospheres. We need to make a rice box to figure out the pressures of all the gases. So here's how we do it. We draw a box, although you don't have to draw a box. We do RICE. So the first thing we do is we write our reaction. Give yourself lots of room. Do not try to make this too small or you'll make a mistake. The next thing we do is we write our initial concentration. So in this problem, we're told that our initial concentration is 0.5 atmospheres of sulfur trioxide, and we have nothing else. 0 sulfur dioxide, 0 oxygen. Now, stoichiometry tells us that when this reaction goes, for every mole of oxygen that I gain 2 moles of SO2, and I lose 2 moles, or I consume 2 moles of SO3. So we're going to write this as minus 2x plus 2x and x, where x is the unknown. We don't know how much reacts, but we can calculate it. Now, when I get to equilibrium, I'm merely taking the initial quantity minus the change. So for every compound in this reaction, I just do a little addition and subtraction. So for sulfur trioxide, I get 0.5 minus 2x. For sulfur dioxide, I get 0 plus 2x, or just 2x. And for oxygen, x. All right, I know the total pressure at equilibrium is 0.650 atmospheres, and that's the sum of all of the partial pressures at equilibrium. So I add them all up. I take all the elements in the E row and I add them together. 0.5 minus 2x plus x equals 0.650, and I just solve for x. And you should get your calculator, do all the math, and you can see that x turns out to be 0.15 atmospheres. So at equilibrium, I'm going to have 0.5 minus 2 times 0.15, or 0.2 atmospheres of sulfur trioxide, 2x, or 0.3 atmospheres of sulfur dioxide, and x, or 0.15 atmospheres of oxygen. And that's it. That's how we do equilibrium problems. We're going to do a lot of these. Part 3. Write the equilibrium constant expression for this reaction and use it to calculate the value of Kp at 1000 K. All right, so here's my reaction. We know we can write from the previous problem, and at this point you should go back to look at the equilibrium reaction. We can write our Kp as SO2 squared times O2 divided by SO3 squared. So now I know the concentrations at equilibrium. I can put those numbers in. So Kp is 0.3 squared times 0.15 divided by 0.2 squared. When you crunch the numbers, you see that comes out to be 0.34. Now we move to the next problem. Section 15.6, applications of equilibrium constants. We have 2SO3 decomposes to form 2SO2 plus O2. We've seen this reaction before. We want to consider each of the following situations for the equilibrium system shown above, and the system is allowed to reach equilibrium at 1000 K. So when I've got each of these initial pressures for SO3, SO2, and O2, the question is, in which direction, toward the left or toward the right, should the reaction proceed in order to get to equilibrium? Right? So when I have 1 atmosphere of pressure of SO3 and no SO2 and O2, we know this reaction is going to move to the right. It's going to form SO2 and O2. On the other hand, when I have 0 sulfur trioxide, but I have sulfur dioxide and oxygen at a pressure that's greater than the equilibrium pressure, we know that this is going to move back to the left to form some sulfur trioxide. And now when I look at this and I see I have 1 atmosphere of each of the 3 substances, I can see that this is also going to move to the left, because my concentrations of SO2 and O2 are higher than at equilibrium. So I've got more products than I really should have, so this will move back to the left to restore my equilibrium state. All right, and I've just recopied this, and we want to define the term reaction quotient, and we call that Q. All right, Q, this is going to be very important, and you'll for sure see this on the exam, both mine and in May. The value obtained by substituting in the reactant and product concentrations into the equilibrium equation at any point of a reaction. So in other words, Q is answering the question, where is the reaction right now? All right? And we want to consider the initial conditions in the third row of the table in part A. What is the value of Q? All right, so Q is just going to be, I take my values in my table, or the values right now, plug them into Kp. Well, 1 squared times 1 divided by 1 squared is 1. And the value of Kp is equal to 0.338 at 1000. So the question is Q larger than, smaller than, or equal to Kp? And of course, the answer is Q is larger than K. 1 is larger than 0.338. So in which direction will the reaction proceed in order to get to equilibrium? And the answer is it's going to move back to the left. All right, we're going to talk more about this issue of Q and K and get a lot more practice, but that'll be in the next video.